Alright, hello everyone, my name is Zach, and in today's video I'm going to be showing you guys how to use Python to model the flow between different tanks. But first, before we get into Python, we're just going to go ahead and I'm going to show you guys the setup of this problem, show you guys what we're working with, and get a conceptual understanding of what we are getting ready to do in our Python coding. So the problem that we are working with right here is we have three tanks right here, and they're going to be filled with some sort of fluid. And these tanks are going to be flowing into each other right here, alright? So we have this first tank right here, alright? And the liquid is going to be flowing from this first one into the second one right here, alright? And the second one, it's also going to have some outside fluid flowing into it from an outside source. And so this tank 2 has two inputs right here. And the fluid from inside tank 2 is going to be flowing inside of tank 3 over here. And the tank 3 is going to be outputting its fluid into no particular area. It's just going to be an output right here. Alright, and the first step we're going to want to take when we're solving this problem is we are going to want to come up with some equations to model these different flows right here. So we're going to go ahead and set up some equations. Now we are already given this model for Qi right here. Qi is going to be modeling just this input that we have in the tank 2 right here, and we are given that equation right here. It's Qi is equal to Kc, which is just a proportionality constant. It's over here. We have Kc, and we are making that equal to alpha. We are going to be using alpha to represent our proportionality constant later on in our Python code, just to make our lives easier. And that is equal to 0.1, alright? So 0.1 is what we're going to be using as our proportionality constant in all of our flow models. And yeah, Qi is equal to that proportionality constant. And that is going to be equal to the desired height of tank 3 over here, which I believe is set at 4 meters. We'll go ahead and take a look at the word problem, and that'll tell us the specific height, but if memory serves me right, it's going to be 4 meters. That's going to be desired height of the liquid. And that is going to be subtracted by H3, which is going to represent the actual height of the liquid. Alright, so we have a desired height minus the actual height right here, and that is going to be equal to Qi. Alright, so now what we're going to want to go ahead and do is we are going to want to come up with equations to represent these three flows right here. Alright, right here, Q12. We are using to represent the flow between the first tank and the second tank right here. Alright, so Q12. Alright, and that's gonna be equal to this proportionality constant alpha up here. And that is gonna be equal to the height of the liquid in the first one minus the height of the liquid in the second one over here. H1 minus H2. And it's going to be H1 minus H2 and not the other way around, because the liquid is going to be higher in this one than it is over here. So it's going to be flowing from this one to this one over here. Alright, it's not going to be going from here to here. It is going to be going in this direction right here. So we're going to do H1 minus H2. And that is all going to be square rooted, this H1 minus H2. So we'll go to the 1/2 right here. Alright, and that is going to be our equation to model this flow right here between 1 and 2. And over here, it's pretty much going to be the same thing, except that is going to be going from 2 to 3. So we're going to go Q to 3 is going to represent our flow from 2 into 3. That is also going to be equal to our proportionality constant. Instead of H1 minus H2 over here, it is going to be H2 minus H3. And that is once again going to be taken to the square root right there, or also to the 1/2 exponent. Alright, and now lastly, the last equation we have to set up is going to be this Q3 output right here. So we'll go ahead and use Q3 to represent that. Get a better looking equal sign right there. That is going to be equal to alpha, and since it's just an output right there, it's just going to be H3 to the 1/2, since there's only one tank we're worrying about. And yeah, those are the 4 equations that we're going to be using to represent. And next we're going to want to derive our equations to find the differential equations that are going to model the flow, because as you can tell, these heights are going to be changing. They're not going to be staying constant. So these equations are going to be changing around, and we're going to need to find the differential equations to be able to model that. Alright, so now what we're going to go ahead and do is we're going to model our differential equations that are going to show how the rate of the flow is going to be changing over time, because obviously the heights are going to be going up and down in each of these tanks. So this flow is going to be changing over time, and we're going to need to come up with some equations to model that change over time. And basically how we're going to be doing that is we are going to be using conservation of mass. Alright, so obviously the water in this system, it has to remain equal, right? You can't just create the fluid out of nowhere, and it can't just disappear. It has to come from somewhere, and it has to go somewhere. All right. And first, before we get into that, we are going to be changing some things around in our equations down here. We are going to need to change these parentheses into absolute values down here in our Q12 and our Q23 equations right here, because if we were to have, say, H2 be bigger than H1 over here, that would give us a negative number, and you cannot take a negative number to the square root. So obviously that would create imaginary numbers, and we can't have that. So we're going to go ahead and put some absolute values over here, just so that we make sure. Because if H2 is at a higher level than H1, say, it would start flowing back this way, and that is possible, and we are going to want to allow that to happen. So to model that, since this is an absolute value, it's going to say that it's always flowing this way. Since it's in absolute values right here, the flow would never be negative, and we don't want that, because obviously the flow can go this way if it's higher over here and lower over here. So to do that, we're going to multiply both of these equations by just the sine of H1 minus H2. And basically what that's just going to do is it's going to multiply all this over here by this, so that if H2 is bigger than H1, this will become negative, and this will all become negative, so that we can have our flow go the opposite direction. And we'll go ahead and do the same thing over here, since we have absolute values in this one. Like so. Alright, and now we are ready to go ahead and start modeling our differential equations. Alright, and the first thing we're going to want to do is we're going to use volume to represent the amount of fluid in each of these tanks. Since that's simple, it's a liquid, so all we'll have to do is we'll just have to take the cross-sectional area of each tank and just multiply by the height of the fluid, alright? And we are given the cross-sectional area of each of these tanks. For the first one, it's going to be 0.5. For the second one, it's going to be 1. For this third one over here, it's going to be 2, alright? And basically what the cross-sectional area is you can think of it as just like we have a cylinder right here, obviously. So the cross-sectional area is just going to be like, it's just going to be the area of the bottom circle or the top circle. It's just the area of the face of the circle of the cylinder. That's the easiest way to think about that. And obviously we'll have some fluid within it. And the height between here is just going to be our h. So the distance between the bottom of the cylinder to the top of the liquid level, that's going to be our h right here. And our h is going to be changing over time, right? Because it's going to be going down as water flows from this first tank over here to the second tank right here. So we are not going to be able to use that as a constant, because that's going to be changing over time. Our cross-sectional area of each tank is going to be remaining constant, so that is just going to be A. We'll just use that. We'll just use the label for our cross-sectional area of these as A. Alright, so we're going to go ahead and get into modeling these differential equations. We're going to go ahead and erase these right here. Alright, and we're just going to go ahead and we are going to model tank 1. Alright. So we are going to have the cross-sectional area, A1, is going to be multiplied by the derivative of H1, which is going to be the height over here of the fluid in tank 1. We'll go ahead and erase our little diagram over here. Times H1 dt. Alright, and that's just simply going to be equal to negative Q12. That's a Q right there, because that is the only thing coming out right there. Alright, there's nothing going into tank 1, and the only thing going out is Q12, so it's simply going to be negative Q12 right there. Alright, and then we'll go ahead and model the differential equation for tank 2. And that is going to be equal to the cross-sectional area of A2. And that's going to be multiplied by the derivative of the second fluid height of tank 2 with respect to time. And that is going to be equal to Qi right there, since that's coming in, so we want that to be positive. Qi, and that's going to be plus Q12, since that is coming in. And that's going to be subtracted by Q23 over here, since that's going out. Like so. Alright, and now finally we just have to model tank 3. Like so. Alright, we're going to go ahead and do same thing as the first two. We're going to go the cross-sectional area of this third tank right here is going to be multiplied by the fluid height as it is changing over time. And that is simply going to be equal to Q23 minus Q3 over here. Since there's only one input and one output, this is going to be subtracted by that. So we'll go Q23 minus Q3. And there you have it. These are the differential equations we are going to be using to model the flow as the heights of the fluids change over time. And now we're going to go ahead and get into coding this in Python and modeling this whole equation right here. Alright, so we are over here in Python now, and I'm going to be showing you guys functions that you can use to model the flow and the change in height of the liquid between all of the different tanks. And basically what we're going to want to do is we are going to want to create a graph that is going to show how the height of the liquid is going to change over time for each tank. So we're going to have 3 line plots, one for each tank, and it's going to be plotting time on the x-axis, and it's going to be plotting the height of the liquid on the y-axis. Alright, so the first thing we're going to want to do over here is we have imported all of these systems that we're going to be using over here already. We've already gone ahead and done that, and basically what we're going to want to do first is we're going to want to input all of our constants that we have. Alright, so the first thing that we are given was the proportionality constant, right? That's going to be 0.1 for each tank. So we're going to go ahead and go A1, A2, and A3, and we're using A because we called it alpha earlier in the video, and that is going to be equal to 0.1. And then we also had Kc, which is our proportionality constant for the Qn equation, which was the input into the second tank, and that was also equal to 0.1. Alright, and then we had the cross-sectional area of each tank, which was just the circle on the bottom. We were given the areas for that. It was, I believe it was 0.5 for the first one, 1 for the second one, and 2 for the second one. So we'll go ahead and input that. So we'll go A1, no, we'll go down here, we'll go capital A1, capital A2, and capital A3, and that is going to be equal to, actually up here we need to go ahead and do some commas and go 0.1 like that, since we are doing 3 over here, so we need to do the same. Alright, and then this is going to be 0.5, then 1, and then 2. And then we are also given the initial height of the liquid in each of the each of the columns, and that was also the same as the cross-sectional area, which was 0.5 in the first one, 1 in the second one, and 2 in the third one. So we're going to go HI1, go high 2, and high 3, because this is going to be changing over time, so you don't want to just call it height. We'll go ahead and call it height initial, or high for short. And that is also going to be equal to 0.5, 1, and 2. And then we also had a desired height that we want the third column to reach. All right, we want the third column to reach a liquid height of 4. So we'll go ahead and enter that. Well, that will be H3 and then set point, and that is going to be equal to 4. We want it to reach a height of 4 meters. All right. And we're going to want it to stop running the calculations we're going to be doing after a certain time, and we'll do a 500 for that. So we'll t end is going to be equal to 500. So we're going to be letting it flow, the flow go through the system for 500 seconds. That's basically what that's going to mean. All right. And there we have all the constants we're going to be using for our equations. And now we're going to get into our first function. We're going to call this RHS for right-hand side. And basically, this is going to be taking two inputs. It's going to be taking the time and the y. All right, so our t is going to be the independent variable, and then our y is going to be our dependent variable. That's going to be representing the heights of the fluid. All right, and then get that outside the parentheses there. All right, so H1, H2, and H3, that's going to be equal to our y. We want the y to represent the heights, all right? And basically what we're going to be doing is we're just going to be inputting all of the equations we did at the very beginning of the video to represent the flows, our Q12, our Q23, our Q3, and our Qn. We're going to input those right now. Excuse me. We're going to go Q12. And that is going to be equal to, as you remember, it's going to be equal to the NP dot sign. And that is going to be equal to H1 minus H2. And then that is going to be multiplied by, I believe, alpha 1. Actually, we just have it as A1 up there, right there. That's going to be multiplied by 0.1. And then that is going to be multiplied by the np.abs, because we want it in absolute values, because this is going to be getting square rooted and we don't want that to be negative. And that's going to be h1 minus h2. Alright, and then we'll get some parentheses going around this. And that's going to be square rooted. Like so. Let's just check here, make sure we did all this right. Yep, that's looking good. And then we're going to come down here and we're going to do pretty much the same thing for Q23, except we're going to substitute H2 in for H1 and H3 in for H2. Alright, we'll go ahead and call this one Q23. That's going to be 2 and 3. This is going to be A2 over here. And this is going to be 2 and 3. Alright, and then we'll come down here and we'll do our Q3, which is just the output at the end of the third tank, if you remember the diagram from earlier. And that is going to be equal to A3, and that's going to be multiplied by, let me see here, that's going to be H3 to the square root, or to the 1/2 power. Yeah, these should all be 1/2 over here. That was my fault. To the 1/2 and to the 1/2 over there. Alright, so we have all these. Now we just need to do our Q input, which is just going to be Qi. And that was going to be equal to our Kc, which was the proportionality constant for the input. And that is going to be H3 SP. Actually, we had a capital H, H3 SP, minus h3, like so. Alright, there we go. Now we have all of our equations in that are going to model the flow between them. Alright, and now we are going to return our differential equations that we did at the later part of the first video when we were doing our diagramming. And we are going to want to solve for the change in height over the change in time. So basically we're just going to take those equations, do some algebra, and divide the cross-sectional area over on both sides so that we just get the dh dt by itself. And what that's going to leave us with is, for the first one, it's going to be negative q12, and that's going to be divided by a1, which is our cross-sectional height for the first one. And then for the second one, let's see here, what was it? It was q12 plus qi, and then that was subtracted by q23, and that's going to be all over a2. Alright, and then for our third one, we just have, let's see here, q23 minus q3, and then that is all over a3. Alright, and so that is our first function, and now we are getting ready to run a function that is going to solve these differential equations over here for a whole time slot, which is going to be our 0 through 500, and we're going to go ahead and get into that now. Alright, so we did make a tiny little syntax error over here in our RHS function. We did include an extra parentheses over here on accident, so we'll go ahead and get rid of that. Make sure it's running good. Yep, there we go. Alright, so now we are going to get into our solve IVP function, which is basically what we're going to be using to solve these differential equations over here. It's going to be doing all of the math for us so that we don't have to. And we're going to go ahead and hop into that. So we're going to go solve IVP. And basically it's going to solve our RHS over there. And it's going to be doing that over a certain time period. It's going to be solving it for the whole time period. And that's going to be from 0 to 500. Alright, and we are going to supply that with our initial heights over here that we had. So we'll go HI1, HI2, and HI3. Alright, and then we are going to be using the Rodal method, which is just a certain mathematical method that's going to be using to solve these differential equations. So we're going to go method is equal to Rodal, I believe. Hopefully I'm spelling that right. If not, we'll come back to it. Alright, and then we'll have the dense output is going to be true, so we can get our values back right there. Alright, and then that should be good for that function. Let's see, what do we have here? HI3 is not defined. I'll need to come up here and put that in. Alright, let's run all that. Alright, do we need, let's see, let's capitalize that. Alright, so we did forget to capitalize the R over here in Rodal, so we'll go ahead and do that. And then over here we also did forget to click the multiplication sign so that it knows it needs to multiply these things together. So we'll get that. And there we go, our function is running all nice and dandy now, alright? And so now what we'll go ahead and do is we'll go ahead and set this equal to solution, so that we can have something to call to for our graphs later when we're wanting to plot all this. And we'll go ahead and do .sol over there. Alright, there we go. And now we are ready to go ahead and get to graphing. So what we're going to do first is we're going to want to get our x-axis going, which is going to be our time. So we're going to go tplot. And we'll do a linear space over here. We'll go ahead and do np.linspace. And that is going to be from 0 to our t end over here, which is going to be 500. And then we'll do 500 points so we can get a point at every second. Alright, and those are going to be our values for the x-axis right there. And then we'll go ahead and do, we want to get our values for the y-axis, which is going to be the heights of the liquids within each of the cylinders. We're going to do 3-line plots on the same graph, one representing each cylinder. Alright, so we'll go ahead and do H1 plot, and that is going to be equal to, actually we'll go ahead and do, we'll do them all at the same time, just to save space. So we'll go H1 plot, H2 plot, and H3 plot. And that is going to be equal to solution T plot. So that is going to run through this function right here at all of these given times right here, and that's going to give us our values for the heights of the liquid within each cylinder. So we're going to go ahead and make our plot. So we're going to go fig is equal to make subplots. And then for the first one, we're going to do fig dot add scatter. And then the x is going to be our time, so that's going to be t plot. Only want one right there. All right. And then our y is going to be equal to our h1 plot over there. Get that underscore. Alrighty. And then our mode is going to be equal to markers. And then for our name, we're going to do h1. See if that's working. Alright, looking good, looking good. Alright, now we'll go ahead and copy this on down 2 more times, and we'll change this around for H2 and H3. Get that going in there. Alright, change this to the second height plot for our second cylinder. Get that going as H2. Then we'll get that going as H3, and we'll also name it H3, and yeah, that should be good to go. Let's see how she's looking here. And yeah, there you have it. Let's see. Actually, we're going to want to do lines here instead of markers, just so it looks clearer and is better to look at. So we'll go ahead and get this changed up to lines over here, just so we don't have all this empty space over here. We'll do lines. Alright, and there you have it. That is going to be the graph of the height of the liquid within each cylinder as time moves on. As you can see here, the height for the first and second column are relatively about the same. Let's see, around 150 seconds, the height steadies out and it stops kind of changing, and it just kind of finds a height that balances out all the equations. And for H1 and H2, it is about 4.87 meters over here. As you can see, it changes a little bit, but not too much. And then for the third column down here, it's about 2.43 meters. We wanted that to be around 4, right? That was our condition that we were trying to solve for. Is we wanted to solve this for when the height of the liquid within the third column was around equal to 4. But obviously this this problem we were solving today was incredibly simplified from what it would be in real life. We had our proportionality constant set to 0.1, and it was 0.1 throughout the whole reaction. Usually you can get that to be a lot different and model it a lot more complicated, and you can get this to be equal to 4, but we are not going to be going over that in today's video. This is all we're going to be doing in today's video, is just this 0.1 proportionality constant, but it is possible to solve this for 4, but that involves a lot more complicated methods that we're not going to be getting into. And we're just going to stick with this for right now. And that is going to be the end of today's video. That is how you create a diagram and model the the change in flow of liquid between several columns interacting with each other, and yeah. Hope you have a good one. Make sure to smash like and subscribe, and yeah, I'll see you next time.